Good day, everyone. So we're reviewing Wetzel's Limnology textbook. This is edition number 4, and we're focusing on chapter 12 right now, looking at salinity and ionic composition of inland waters. And right now we're looking at calcium distribution in lakes. And where we left it at yesterday was the review of this figure 12-9. So A, we have two figures. We have A and B. A is depth time distribution over 2 years of calcium concentration in a saltwater lake. Lake 239 in Canada. So reminder, soft water is for diluted ionic composition, and where the salt is originating from acidic igneous rocks. So, and then B, we have a hard water lake. So hard water lakes are dominated with calcium and magnesium ions for fish lake in the US. And then the gray rectangles in the panel, B show the duration of ice cover, so those are like the ice cover. And then on fish lake, contour lines interpolated between manual samples, the black dots. So all the black dots represent manual samples, and those lines here, the contour lines, are interpolation between the black dots. And on the x-axis, we have time. So for the soft water lakes, what we're seeing here is we have concentration at the 2 milligrams per liter, and as we were expected, it's not very high in calcium because it's soft water lake, and we have like also even like a pretty low concentration in time period with this, which is probably like maybe in January or February on the lakes, although they don't mention any ice cover for that lake at that time. And then for this lake, this is the hard water lake. So here, as expected, we have pretty high concentration of calcium. Of course, magnesium is not plotted here. And we also have in the epilimnion as well as the metalimnion, we have a decrease of concentration of calcium during the summer month. And that is due to the fact that you have photosynthetic organisms that are changing the pH of the lake, and you have precipitation of calcium carbonate due to the change in pH of the lake due to the presence of those of the plants and the effect that they have upon the pH. So let's start on the text here. So epilimnetic decalcification is reflected simultaneously in the distribution of bicarbonates of hard water lakes because concentration of magnesium, sodium, potassium, and chloride are relatively conservative, as discussed further on the specific conductance follows. The specific conductance follows changes in calcium and bicarbonate concentration in nearly a 1-to-1 relationship. A portion of the precipitation of the precipitating calcium carbonate is resolubilized in the hypolimnion, which is reflected in both the increased concentration of calcium and the specific conductance in hypolimnetic waters. Some of the calcium carbonate is entrained permanently in the sediment and commonly constitute greater than 30% of the sediments by weight in moderately hard water lakes. Adsorption of organic compounds to calcium carbonate lowers the pH, the rates of dissolution in hypolimnetic strata of reduced pH. Further calcium complexes with humic acid, especially in the sediments, alter exchange equilibria in the hypolimnion. Biogenically, induced decalcification of the epilimnion reaches an extreme in very productive hard water lakes. For example, the calcium concentration of the epilimnion of hypereutrophic wintergreen lake were reduced from nearly 50 milligrams per liter to below analytical detectability in a few weeks. The magnitude of this loss from the trophogenic zone and the resulting increase in monovalent divalent cations ratios should be recalled in the subsequent discussion of the effect of the calcium content and of cationic ratios on species distribution. Magnesium. Magnesium is required universally by photosynthetic plants for the magnesium porphyrin component of chlorophyll molecules and as a micronutrient in enzymatic transformation, especially in the transphorylations by algae, fungi, and bacteria. The demands for magnesium in metabolisms are minor in comparison to quantities generally available in freshwaters. For example, a large phytoplankton population of 1,000 micrograms of chlorophyll A per liter would be sustained by concentration of 30 milligrams per liter. For example, a large phytoplankton population of 1,000 micrograms chlorophyll A per liter would be sustained by concentration of 30 micrograms per liter. The low availability of magnesium has been implicated as one of several factors influencing phytoplanktonic productivity in an extremely oligotrophic Alaskan lake. However, such conditions are exceedingly rare in comparison to limitation imposed by the restricted availability of other nutrients. Before we move on, let's look at this figure 12-10, depth time series of major ion concentrations, calcium, sodium, magnesium, chloride, sulfate, and bicarbonate in Lake Kinneret, Israel from 2002 to early 2003. Contour lines interpolate between manual samples, white dots. Adapted from cuts, etc., potassium is not shown as concentration were constant between 0.179 and 0.198 milliequivalents per liter over this time period. We have depth on the Y, and then we have time on the X, and then we have the concentration in blue, and then we have the interpolation, and then the time of sampling are those little white dots here. That's when the samples were taken for a specific month or during the month, for a specific month. So calcium, so it looks like it's probably a hard water lake. It has pretty high calcium concentration. Let's look at the magnesium. Yeah, magnesium is not, extremely high, but it does have, it's like 2.9 milligrams per liter. Sodium, so sodium is pretty high. So maybe also a lake that is close to the coast. I'm not sure. And then chloride definitely as well. And then we have some amount of periodicity here. We have, for example, chloride concentration pretty high in the February time period, but decreasing during the summer. Sulfate is pretty low throughout the year. It's even very low like in the fall. We already went through sodium. Magnesium, it's pretty high in the February time period, the way chloride was. And then bicarbonate is actually kind of a mirror image, a little bit of calcium, and which makes sense because calcium carbonate basically like a species that would buffer this lake. So bicarbonate is one of the buffering capacity of that lake. Magnesium compounds are much more soluble than their calcium counterparts. As a result, a significant amount of magnesium rarely precipitate. The monocarbonates of hot waters are usually greater than 95% calcium carbonate under ordinary CO2 pressures. Magnesium carbonate and magnesium hydroxide precipitate significantly only at very high pH, greater than 10, under most natural conditions. The concentration of magnesium are extremely high in certain closed basin saline lakes. Because of magnesium solubility characteristics and its minor biotic demand, concentration of magnesium are relatively conservative and fluctuate little both in saltwater streams and lakes and in hot water streams and lakes. This attribute has been used to advantage by employing the magnesium budget of inputs and outflows to determine groundwater influxes to a lake by magnesium mass balance, sodium, potassium, and minor cations. The monovalent cations, sodium and potassium, are involved primarily in cellular ion transport and exchange. An absolute sodium requirement has been demonstrated in only a few plants. The sodium requirements are particularly high in some species of cyanobacteria, and sodium is required for photosynthesis, bicarbonate transport, intracellular pH regulation, nitrogen fixation, and nitrate reduction and uptake of phosphate. The highest reported sodium requirement for phytoplankton is 4 to 5 milligrams per liter for a cultivated Dolichospermum anabaeum, but many other algae and cyanobacteria have much lower thresholds. Potassium and other monovalent cations, namely lithium, rubidium, and cesium, cannot substitute for sodium. The potassium limitation of phytoplankton is unlikely to occur in nature. In an experimental study, the growth of the freshwater diatom Asterionella was unaffected above 27.5 micrograms per liter, and other diatoms. a diatoma elongatum and cryptomonad plagioselmis nanoplantica were unaffected above 31 micrograms per liter. I'm not sure what the K stands for. We see in the K and then we see the M here. Like, I'm not sure what that stands for because we have the units here per liter. Oh, I see. It's the atom. So this is 30 micrograms of magnesium per liter instead of putting the magnesium first. But anyway, okay, got it. Cyanobacteria possesses separate systems for the active transport of both carbon dioxide and bicarbonates. The active transport system for molecular CO2 assimilation is so efficient that extracellular CO2 concentration are reduced far below the equilibrium values by a transport system that recognizes molecular CO2 and transports it into the cells. Cyanobacteria also possesses active transport system for bicarbonates. The bicarbonate transport system occurs in cells or growing at low concentration of extracellular CO2, although bicarbonate transport appears to have no effect on CO2 transport, and CO2 transport appears to have no effect on bicarbonate transport. One of the bicarbonate transport system is dependent on the presence of millimolar concentration of sodium. The active transport of CO2, however, requires only micromolar levels of sodium. Therefore, sodium, only along with many other factors, can influence the development of cyanobacteria. Sodium and potassium occur in relative abundance as highly soluble cations of numerous salts, and their spatial and temporal distribution in lakes is relatively uniform. Alteration of their concentration in natural waters is not common except under conditions of pollution, for example, salinity from industry, road deicers, water softening, or agricultural fertilizers. Only small seasonal variations are observed, particularly for sodium, in accordance with the conservative nature of these ions. Moderate epilimnitic reduction in potassium concentration have been observed in productive lakes and in fertilized productive farm ponds. This reduction is related to potassium utilization by the massive algal population and by submerged macrophytes and their epiphytes. Potassium is actively assimilated into submerged plant tissues with a light-dependent exchange process of reciprocal sodium efflux. Lake sediments are net sources of potassium during summer stratification, and some hypolimnetic enrichment and export occurs in stratified eutrophic lakes. The concentration of rarer alkaline earth and alkali cations of natural waters vary considerably in relation to the lithology of the drainage basins. Their distribution is discussed by, etc. General ratios of major to minor cations are given in Table 12-6. Strontium cycling is closely coupled with calcium, and strontium and calcium ratios maintain a nearly constant stoichiometry. Nutritional requirements for these relatively rare elements have not been demonstrated, although they can sometimes substitute for the major cations in metabolic pathways, chloride and other anions. Earlier discussions of the general distribution of chloride ions in lakes emphasize that chloride is usually not dominant in open lake ecosystems. Streams and lakes near maritime regions, however, often receive significant input of chloride from atmospheric transport from the sea. Anthropogenic sources of chloride can greatly modify natural concentration so that salinization is an emerging global threat to freshwater resources. In North America, many north temperate lakes in urban areas have seen a rise in chloride concentration from road deicers. Figure 12-11A shows the rise in chloride concentration in Lake Mendota, US, primarily as a result of road deicer inputs. Analysis of Lake Constance, a large 254-meter deep European lake, revealed that the threshold increase in chloride concentration was a result of road salt, 52%, wastewater, 23%, farming, 11%, soil weathering, 9%, and precipitation and solid waste incineration, 3%. Chloride is influential in general osmotic salinity balance and ion exchange, but variations observed in many lakes are associated with the hydrology of the basin and seasonal fluctuation and not metabolic utilization. Okay, so 12-6, table 12-6, we have approximate ratios of minor alkaline earth and alkali to sodium and calcium. So as they were saying, the calcium to strontium ratio, for example, is very conservative. So we have sodium to lithium, sodium to rubidium, sodium to cesium ratio, and so those are the values. And then we have calcium to barium, calcium to strontium, calcium to beryllium, and then calcium to radium. What we can glean here is, like, for example, calcium to barium is very close to each other. So the occurrence of barium is close to calcium in a lake, where it's opposite, for example, for calcium to beryllium or calcium to radium, of course. And then this figure is chloride concentration in milligrams per liter in Lake Mendota and Lake Constance in Europe. So the y-axis is the chloride concentration in milligrams per liter, and the x-axis is the time series. So this is a very long time series. This is more than 60 years of data. Maybe even 70 years of data. So we see a rise, a constant rise of chloride concentration, and as we were presenting in the text, a lot of it is due to the de-icing input from the roads, as well as other inputs such as wastewater. So as the population increases and the road density increases, then you have higher concentration of chloride that ends up in those lakes because of the erosion of the salts from the road, and that it is entrained in the water that ultimately ends up in the lake. And here we have Lake Constance. So this is a pretty deep lake, and so the chloride concentration is on the y-axis. Then we have time on the x-axis, and then color-coded is the concentration. The color-coded is the depth. So what we are seeing here is that we have pretty high concentration at very high depths of chloride, which is not necessarily the case. We have low concentration, so we have up to, and once again, it shows an increase, and that is due to increased de-icing and increased network of roads that requires de-icing, as well as probably some amount of accumulation of that chloride, because it's not really needed in a lot of metabolic pathways. So it's probably accumulating in the lakes for that purpose, in the waters of the lakes. And so we have concentration up to 7 milligrams per liter, which is a fair amount. All right, so concentration of minor halides vary somewhat with the lithology within the drainage basin, and higher concentration often occurs in lakes and streams in proximity to marine regions or in those that possesses marine rock formation within their drainage basins. Boron is of limnological interest because it is a macronutrient required by many algae and other organisms. Concentration of boron in natural waters are relatively high in comparison to other minor elements. The average concentration in the ocean is 4.6 milligrams of boron, but typically less than 0.5 milligrams of boron per liter in fresh waters, with major sources being sea salt, aerosol production, volcanic production, and anthropogenic activities. Concentration reached exceedingly high levels, 1 gram of boron in certain closed saline lake, as is the case with most macronutrients. High concentration are generally toxic to most organisms, as was exemplified by the well-known excessive use of the macronutrient copper as a biocide. So here we are looking at table 12-7. We're looking at approximate average concentration of halide and boron in natural freshwaters. So chloride, fluoride, and then we have the chloride ratios: chloride to fluorine, chloride to bromine, and then chloride to iodine. So definitely, chloride takes a lion's share in terms of its prevalence as an ion in the waters, natural fresh waters in this case. So why don't we leave it right here, and we'll pick it up tomorrow with subsection E, cation ratios. Thank you, and I'll see you tomorrow. Bye.